Okay, all of that was off the record. Sorry. Thank you. Thank you for reminding me. Last semester I went all the way through the whole lecture one time and forgot to record. Thank you. Yeah, we missed 20 minutes. Okay. And every problem, it is whether I ask for it or not, it really is implicit that you need to check that the steel that you have chosen or the steel that has been given to you, either way, you need to check that it is more than the minimum steel, it is less than the maximum steel, or that epsilon sub t is at least 0.005. You need to make those checks on every problem. And you need to always show me that phi min is greater than mu. I want to reiterate that now that you've done a few homeworks. It is not sufficient to calculate the area of steel from a row equation or the Rn tables in the back of the book. It is not sufficient to get an area of steel required, provide an area of steel that is more than the area of steel required, and finish the problem and think that's the end of the problem. No, you always must prove to me that phi min is greater than mu. No problem is finished without that step.
Professor, is there an exception? I think you just mentioned 10 minutes ago on homework 4, problem 2, part A. We're not looking for phi min, we're looking just for the allowable live load to check the area, minimum and max. I mean, it's not a problem to find phi min. I just,
Oh, you guys are sharp. Fine, you found the one exception. No, what you're going to find is all you're going to do is reverse engineer it. So you're going to have to find phi min, and then you're going to equate mu to phi min, and then you're going to take the factor dead load out of mu to figure out how much live load is left, and then divide by the live load factor to get to the actual allowable live load. So in effect, you really are checking phi min is greater than or equal to mu. You're just reverse engineering mu. But yeah, you did. You found the one exception. So good for you. Shoot, I can't think of anything else. Did anybody have any questions? If you checked your homework and you say, why did he dock me for that? Why did I lose points on this? What did I do wrong? Please go ahead and ask me.
Professor, this is not about that, but for homework number 4, 3, part A, do you want us, whenever we get the live load, do you want us to do the 1.2 and the 1.4 for it too, for the LRFD? So we still divided by the 1.4 to have the actual live load that's going to go on it?
Everything you said is spot on, except for the live load factor is 1.6, not 1.4.
Oh, sorry, 1.6, my bad, yes.
Yeah, and I wanted to clarify that because there is another load factor that is 1.4 dead, 0 live. And for this particular problem, do not worry about the 1.4 dead, 0 live. Obviously, that doesn't apply if you're trying to find the allowable live load. So, but yes, everything you just said, you are going to solve for phi min. Phi min is equal to mu. You take out of mu the factor dead load. That leaves you with the factored live load. Divide by the live load factor to get the actual allowable live load.
All right, got it. Thank you.
Okay. All right, so is everybody ready to continue the compression steel lecture then? Okay. Example, wait a minute. Let's make sure I'm starting in the right place here. Example 3. Oh, I didn't go back far enough. Example 3. I think this is right. Okay. Okay, I think this is where we left off. Let me just double check one thing here. That was lecture 7. Yeah, okay. All right, so here's the problem. We have this beam. So far, it only has tension steel. All the dimensions are given to you. The strength of the concrete is 3,060 KSI. We want to design this beam to carry an MU equal to 650 kip feet. We cannot change the beam dimensions. We are constrained to a 25-inch deep beam. So we want to find the area of steel that will carry 650 kip feet. Please, somebody stop me if I've already done this example. I think this is where we left off.
This is where we left off, yes.
Okay, perfect. Okay, so for our solution, we're going to start by, for all design problems where we don't know the area of steel, we're going to start off by figuring out our R sub n index, where we put in mu over phi b d squared. Again, everything in this problem is defined, so we just put in b and d squared, and we get 895 KSI. So Rn is 895 PSI. Using table 8.12, the maximum value for Rn is equal to 685 PSI. So if you get your text, which I have laying around here someplace, there we are. Okay, so if you have your textbook and you go to table A12, it's on page 606 of your textbook, and you go all the way to the right-hand corner, all the way down to the lower right-hand part of the page, you will see that mu over phi bd squared does not go any higher than 685. And why is that? Because the rho at 685 is 0.136, which according to table A.7, 3,000 psi, 60 ksi, rho when epsilon sub t equals 0.005 is 0.136. So that means that for 3,000 psi concrete, 60 ksi steel, I can't go any higher than Rn equal to 685, but I need 895. What do I do? What can I do? So the answer is I have maxed this beam out with tension steel. If I put any more tension steel in here to get closer to this strength, I'm over reinforced. And over reinforced I cannot be. But if I put compression steel in the top, then I can put more tension steel in the bottom and be able to carry more load. So the answer is I have to put in more compression steel. And again, using table 8.7, rho equals 0.136 when epsilon t equals 0.005. That's why they stopped the table at 685. So as required is rho BD. So I put in my maximum rho value, 0.136 times B times D, and I get 5.98 inches squared. So I choose 6 number 9s. AS is 6 times 1 inch squared, 6 inches squared. Little a is ASFY over 0.85 F prime CB. I put in my 6, 60, 3, and 20. I get 7.06 inches. If F prime C is 3000, beta 1 is 0.85. So C is A over beta 1, 706 over 0.85, 8.30, epsilon T, 22 minus 8.3, 0.00495. So again, we are right up against that limit of 0.005. V is 0.896. And so with my 6 number 9s, my capacity is using the singly reinforced rectangular beam equation. And I plug in 6 times 60 over 1.73 times 20, 22 minus, I get 5958 or 496 kip feet. That's my maximum. I've put in maximum steel. I'm right against my maximum steel ratio, and I only have less than 500 kip feet of capacity. I need 650. So 496 less than 650, design is unacceptable. My epsilon T is already below 0.005, so I can't just add more tension steel. So I need to add compression steel. Like we did for T-beams, we break the problem into 2 parts, MN1 and MN2, for the portion resisted by tension steel and the portion resisted by more tension steel balanced by compression steel. So I break the beam into 2 beams. One beam is flexural steel balanced by concrete. The other beam is flexural steel balanced by compression steel. The total steel in the beam is going to be AS1 plus AS2, but we're breaking it up into 2 parts so that we can design it appropriately. So AS1 plus AS2 is my total steel A sub S. AS2 is equal to AS prime. So the flexural steel on this side is perfectly balanced by the compression steel. So I can solve for MN1 is equal to AS1 times D minus A over 2. That's this half. MN2 is AS2 times D minus D prime. That's the other half. MN1 plus MN2 is equal to the total MN. Therefore, VMN is equal to MU, which it better be when we're finished. So MN2 is equal to MU over phi minus MN1. So let's add some compression steel. D is at 2.5 D prime. So we can solve for how much capacity we need in this beam by taking the total demand, MU over phi minus MN1. So I take 650 as my total demand minus my 496. Why did I put a phi in there? I think that's a typo. 496 already had phi on it. Okay, let's see. Does that work out? Minus 496. Divided by, actually, minus 496 divided by 0.9, 171. Okay. Oh, I think I know why I did that. I divided the demand by phi, and this had already, oh, okay. I got it. Sorry, guys. Took me a minute to re-engineer that. The 496 is VMN. If I go back, right there. Phi Mn is 496. So when I get here, this is correct. It's mu divided by phi minus Mn. The 496 was phi Mn, so I divided it back out by phi to get back to Mn. That's what that was. Did I lose anybody on that? Is that clear? Okay, I assume everybody's okay.
Yes.
Okay. So Mn2 is 171 kip feet. So saying it in different words, the portion of the tension steel that is balanced perfectly by the compression steel must support at least 171 kip feet. Because the rest of the tension steel balanced by the concrete is good for 496 kip feet. All right, so now that I know I have to carry 171 with my compression steel, then I can solve for how much steel I need. 171 times 12 inches per foot over d minus d prime divided by 60 KSI is 1.75 inches squared. So that's how much compression steel I need. I'm going to choose 2 number 9s, which gives me 2 square inches of steel. So AS is equal to AS1 plus AS2. I had 6 inches squared, plus I added 2 inches squared for a total now of 8 inches squared. So I'm proposing to have 2 number 9s up here and 8 number 9s down here. Rho is equal to 8 over 20 width times d, b times d, 0.01818. Rho prime, I don't know why those primes don't show, but rho prime is 2 inches squared over the same BD, 0.00455. Now I'm going to do my test. And so I have 0.1818 minus 0.00455 is 0.1363. My test, I have to fill in beta 1, F prime C, D, D prime, and Fy here. That gives me 0.1323. So rho minus rho prime is larger than this test, and therefore my compression steel will yield. So if the compression steel yields, then I can just plug in Fy. I don't need to solve for the stress in the compression steel. I can just plug Fy straight in. So the force in my compression steel is 2 inches squared times 60 KSI, 120 kips. The tension in my tension steel is always ASFY. 8 times 60 is 480 kips. And so little a is the tension minus the compression steel over 0.85 F prime CP. 480 minus 120 is 0.85 times 3 times 20, 7.06 inches. Big C then is 0.85 F prime C B times A. Plug in my 7.06, I get 360 kips. And I better, because the compression steel plus the concrete in compression should add up to the tension. All of your forces need to add up to 0. So, and they do. 120 plus 360 is 480. Okay, so just repeating these numbers here. To find the capacity, we sum the moments about the top of the beam. T sub D, C times A over 2, C sub S times D prime, 480 times D of 22, minus 360 times A over 2, minus 120 times D prime is 2.5. I get 8989, or 749.1 kip feet. C is A over beta 1, 8.31 inches. epsilon T, 22 minus 8.31, 00494. It is less than 005, so I need to check my phi. This equation is epsilon sub t minus epsilon y over 005 minus epsilon y, 0.895. So I'm just taking a very small penalty. So phi min is 8.895 times 749.1. I get 670.4 kip feet, greater than 650 kip feet, and so the beam is adequate. Okay, so that's our last example for compression steel, and I'm sure I must have some questions. Okay. Jesus, I am glad you asked that. Somewhere in here. And you guys have access to these lecture notes from Blackboard. So I think it was example number 2. I know it was last Thursday, but example number 2, we did this analysis problem where I had 6 number 8s in the bottom, 3 number 7s in the top. And we calculated rho, and we calculated rho prime, and then we did our test. So if rho minus rho prime is greater than this value, then the compression steel will yield. And in this case, we had 0.1548, which was less than 0.1922. So in this case, the compression steel will not yield. So this is example 2. You can go back and study this example. But I'm glad you asked that because we kind of fragmented this lecture between these two ideas. So this is what you do if the compression steel will not yield. You need to write your equations. You have 3 forces on this section. You have the tension steel, you have the compression steel, and you have the compression in the concrete. You need to write all 3 forces in terms of little c. So the compression steel is equal to the area times the stress. And the stress is equal to this expression here, which is 87 KSI times C minus D prime over C. So this expression is the stress times the area. And this is in terms of C. So you leave this, C is an unknown. Then you solve for T. T is just straight up a number of kips. And capital C, the compression in the concrete, you can also write in terms of little c, like so. Now you sum these 3. The 2 compressions have to equal the tension. So you get a quadratic equation for little c. You solve the equation. There's going to be one positive root and one negative root. You take the positive root, that's what c is equal to. Now that you have c, you can go back and calculate each one of the 3 forces, like so. You have compression in your steel, tension, compression in your concrete. Once you have the 3 forces, you sum your forces about the top of the beam to find your nominal moment. Does that answer your question, Jesus? Okay, great. So, yeah, so compression steel is kind of broken up into, first of all, 2 classes. You have analysis and you have design. On the analysis side, you can either have your compression steel yields, in which case you already know what Fy is equal to, and then you can just get your 3 forces rather directly. sum your forces, get your nominal moment. Or you could have that your compression steel does not yield, in which case you have to write your equations in terms of little c, solve the quadratic, and then get your forces, and then solve for your nominal moment. Okay, so that's your analysis, is either the steel yields or the steel doesn't yield. That's how it goes. For your design, your designs follow like what we did on example number 3, where you have this load that you have to be able to carry. If you're able to carry it with just flexural steel, then you would just carry it with flexural steel. You don't need to bother with compression steel. But if you find that you can't possibly get enough flexural steel, tension steel, without being over reinforced, then you have to add compression steel. And to solve those, you do those like example 3 that we just did, where you break the beam up into 2 pieces and you solve for the one and then you solve for the other and you add it all back together. Does that kind of help the flow of how to do these compression steel?
Professor,
Yes.
so I'm looking through the book, and as I'm reading the compression steel section, I noticed that a lot of some of the examples that are given are in some ways quite different as to the example that you just provided. For example 3, what would be like the best, I don't know, example on the book that can be related to it, you know?
Okay, no, I really appreciate that question.
Because some of the like variables that you used were, I mean, to be honest, were very confusing in from my part. I really didn't really understand some of the methods that you used. So if you can help, that would be great.
Of course, that's why I'm here. Well, hopefully I can help. I'll do my best. So you said the examples in the book kind of do it a different way than I just did it. Okay, and I am reading everything I'm asking you guys to read, just so you know. I'm trying to stay like a week ahead of you guys. So I am reading through this myself. And what I'm seeing in chapter 5 for your compression steel section, I'm seeing a example 5.7 and 5.8 are both analysis problems. So for both 5.7 and 5.8, I'm on page 128 or 129. If you guys want to, if you have your books, you can follow along. And for both examples, all the steel and all the dimensions are known. It tells you how much steel you have. It tells you all your dimensions. So 5.7 and 5.8 are both analysis problems. I assume you're asking me more about a design problem?
Yes, something that relates more closely to the example we just did.
Okay. So the design problems that they have, they give you a 5.9 and a 5.10. And let's see what the difference, and that's it. That's all they give you is 5.9 and 5.10. Okay, so 5.9, they give you a demand and they give you all the dimensions, but they don't tell you how much steel you have. So steel AS and A prime S are unknown. So what they did is they took the total demand Okay, I see what they did. Okay, so okay, so for example 5.9 on page 130, 131, they really did the same thing I just did. It might look a little different, but they really did exactly what I just did. They found from the tables the maximum row that you can use before you're over reinforced. That's what I did. In fact, we can follow along right here.
That's the 0.0181, correct?
Correct. Yes.
Okay.
Yes, yes, yes. Okay, so that's what I did. I found the maximum value equal to 685 of 136. We're using different strength concrete, so the numbers are different, but that's what I did. I found the maximum row that you can use, and then they're finding, excuse me, my voice. I gotta stop yelling. They found the maximum row. Then what they found is from the mu over phi bd squared, they found the maximum Rn, and then they back calculated a maximum moment, 804.4. I pretty much did the same thing. I didn't back calculate using Rn, but I came down here and I calculated the maximum moment that you can get with the maximum steel. And that's where we got VMN is equal to 496. They got MN1 is 893.8. And see how they divided it by phi?
Yes.
And that is, let's go down here a little ways. That's what I did right there. I kind of tripped up over that for a minute. Why did I divide by phi?
Oh, so the mu over phi would be the mn, correct? Or
Yes,
oh, perfect. Okay,
yes.
that's really where I got really confused as to what I was looking at. So that really clarified a lot of things.
Good. Okay. Oh, okay, so see what they did. They really did the same thing, but at the bottom of page 130, they said Mn is mu over phi 1144 kip feet.
I
And
see it.
then they said Mn2 is Mn minus Mn1 is 1144 minus 893
And
equals
that's exactly
250.
what you did right there.
And that is what I did right here. Yeah. Yeah, right there. And then from there down, they really did the same thing I did.
All right.
And compression steel has yielded. And oh, and then they made a boo-boo on the next page. See where it says no good? Because they didn't account for the phi factor. And they kind of drew it out a little bit. Okay, now this one, 510, what's the difference about this? That all looks the same. That all looks the same. Okay. Example 510 is the exact same thing, only this is an example where the compression steel does not yield. And they're showing you how to come up with 40.6 KSI, and then the rest of it falls into place. Okay, so I kind of walked you through it. Does that help?
That you did the best thing ever. Thank you.
Okay, great. All right, everybody, we are going to start our shear lecture tonight, but it's 5:56. So what do you say we do like a 9-minute break? We'll come back at 6:05, and then we'll hit the shear lecture. Does that sound good?
Perfect. Thank you.
Okay, we'll see you back at 6:05. Okay, let's get back into this. So for tonight's lecture, we're scheduled to talk about shear. This isn't a terribly long lecture, but I do think this is going to bleed over to Thursday's time a little bit, which is fine. We can take our time through this. We're kind of shifting gears. Actually, we're not kind of, we are radically shifting gears. We're getting away from flexural design. We're going into a whole new topic of shear design. So does anybody have any last minute questions about flexural design before we leave that whole ballpark?
So for the text next week, this is included too, right? Everything up until Thursday lecture is included.
I don't know. It may or may not be. We're getting pretty darn close to a cutoff, and we may have already passed it. I'll have to get back to you on that.
Okay.
But it most definitely will be on the final, so
right.
Still got to pay attention.
Professor, the test was on next Thursday, right?
Yes.
Perfect.
Yes. So, I mean, that's a good question. The test will most certainly cover everything through T-beams, as you've just been given a homework assignment on T-beams. I do not remember if I'm going to put compression steel on it. I'm pretty sure shear is going to be on the next test. So that's just kind of a rough guideline to get you through the weekend. And I'll fine tune it on Tuesday when we talk again.
Professor, also the timing would be 2 hours for the exam?
Yes.
And 3 questions?
I usually do, well, for a 2-hour exam, it might be 4 questions. It's either 3 or 4.
3 or 4, okay, thank you.
Okay. All righty.
Professor,
Yes.
would you give us time for scanning and making it into PDF and sending it in?
Yes.
Okay, perfect. So that doesn't include in the 2 hours. That's
That-
after the 2 hours?
That is correct. Yeah, that is correct. What I did last semester, and we're all, I mean, I'm sure as you can imagine, we were all trying to figure out what we're doing last semester because we got this big COVID thing right through the middle of the semester. I literally had, the first exam was on paper and the second exam was virtual. It was very strange. But what seemed to work pretty good was that I made a test on Blackboard and I made an assignment on Blackboard. Both of them were the midterm. And so what I did was the test, when you opened up the test, it forced you to use Respondus lockout browser, and it opened up and it gave you, for each problem, there was a PDF file. So you clicked on the PDF and it opened up to my normal paper test exam sheet. And so there's the problem, there's the sketch, there's the, here's what's known, here's what's required, that sort of thing. And then the test in Respondus, all it had was a text box for you to put in your answer. So I asked all the students to put their answer for part A, part B, part C, part D, whatever I had, put your answer for each one of those parts in that text box. And make sure that you submit your test with all your text boxes filled in within your allotted time. Now, last semester, the test was 1 hour and 15. This time it'll be 2 hours, but whatever the allotted time was, make sure you fill in all those text boxes because as soon as you run out of time, it's going to close it up and submit it anyway. That's it. You only get that much time. But then I told them, after you have either submitted the test or it submitted itself for you, take all the work that you did on paper, scan it, and upload that to the assignment that's called the midterm. And so when I go to grade it, I will have the test on one screen and I will have your paperwork on the assignment on the other screen. And it was far, far better for all of us, because if the whole test is only worth 50 points and one problem might be worth 12 points. And if you got the wrong answer, you lose 12 points. It's devastating. But if you got the wrong answer, and then I look at the paper portion that you uploaded to the assignment, and I see that really the answer was wrong because you just made one mistake on one step, well, then you lost 2 points, not 12 points. And so that's how we're going to do it. And that seemed to work best.
Okay, perfect. Thank you.
Also, let's say if we're doing problem 1, and then we're halfway, and can we go to next problem and then come back if we're stuck at some point, or we have to finish one problem, everything, and then go to the next problem?
My understanding is that you can jump from problem to problem as much as you like. You can manage your time by going from problem to problem and going back. The only thing that you absolutely cannot do is submit it and then go back and try to change something. Even if you have more time, once you submit, it's off. It's done. And I did have one student who had internet trouble. And so halfway through the test, they lost their internet connection just briefly, but they lost it. And so it submitted for them. They could not get back in. So I gave the class my personal cell phone number and told them, if you have any technical problems that are beyond your control, text me, tell me what's going on. I walked that student through it so that they were able to finish the rest of their test on paper, even though the submitted test only had one answer out of 3 problems. They were able to submit what they did on paper, and they submitted it in a reasonable amount of time, from when the test was finished. It took them 10, 15 minutes to put it all together and scan it. And so I was able to salvage their test by using the paperwork instead of the actual test. Not suggesting you do that on purpose, but that's an extreme example of we can work through technical glitches. Okay, any other questions? Okay, so let's get started and see how far we get on shear design. Okay, so the first thing we're going to teach you about shear design in concrete is that concrete doesn't fail in shear. I know, doesn't make any sense. Concrete actually does not fail in shear because the material of concrete is much, much stronger in shear than it is in diagonal tension. So when we say that beams fail in shear, that's how we will approach it. That's how we design it. We analyze what the applied shear is. We calculate some constructed shear capacity, but it's not actually shear that's failing. It's a diagonal tension. So if I have a beam that is simply supported, and I'm showing the dashed line, this is where my flexural steel is running the length of my beam. In areas of high bending stress in the tension zone, the cracks are vertical. And so what I've got here is my shear diagram, my moment diagram, and there are my cracks at the bottom of the beam due to this applied moment. In areas of high shear, cracks are inclined and approach 45 degrees in areas of pure shear, more like this. So as you can see, the cracks due to pure flexural moment are 90 degrees because flexural moments create normal stresses, and the concrete is weak in tension, so it cracks horizontally. Well, the stress is horizontal due to the normal stress, so the cracks are vertical. As we get out towards the fringes, the shearing stress produces a diagonal tension. So the tension is running in a diagonal. Actual mode of failure is diagonal tension. So if I take a little square, see that little element right there? And I look at this element in a region of pure shear, it's not pure shear. You know, if I go down here, I have a lot of shear and I have little moment, but it's an area that has little moment and a lot of shear. And I look at this element. Are you done? Sorry, guys, I'm dog sitting right now. Actually, my dog is sitting, but anyway, anywho, normally my wife is home and she's in the other room and she takes care of Willow, our black lab here. But my wife is on the road coming home, so I'm dog sitting. So anyway, I apologize for rude interjections into the lecture. Where was I? Okay, here's my element. This is straight back from your mechanics of materials stuff where we talked about plane stress and plane strain. So here's my element. Oh no, I shouldn't have said anything. I don't have a pick. I'll tell you what, for all you dog lovers, when I finish this lecture, I'll stop sharing and then you'll see her in the background. How's that? Oh boy, I'm really getting derailed. Here's my element. Here's my element in pure shear. I have no normal stresses on this like you saw in mechanics of material because the moment is low. So if I do a stress transformation, and remember all this from mechanics, if I do a stress transformation and I rotate my axes, I can rotate them to a point where the tension is at a maximum. And that tension in the material is at a maximum at a 45-degree angle with no applied moment. So if the tension is trying to pull the concrete this way, then it's going to crack this way because it's stretching the concrete apart in tension. Okay, does that make any sense? Okay, I guess not. Well, what's important is that the beam does not want to fail in a vertical plane. That's not how it's going to fail. If you took like steel or even wood and you apply a pure shear to it, then it would shear. It would just fail along that surface in a vertical plane. Concrete doesn't do that. Concrete will not shear across a vertical plane. It cracks along a inclined plane. That's the point. That's the real point of all this. And that's important that it tries to crack and fail along this inclined plane because that gives us something that we can reinforce with steel. Okay? Is everybody tracking? Anybody have questions?
No, it makes sense. Thank you.
Okay.
A quick question. So the diagonal line on the right triangle, is that basically the resultant of the vertical and the horizontal shear?
Yes, sort of the resultant. Yes, it's more specifically, and it's not super important. It's not like in order to understand concrete shear design that you really, really have to understand this. It's just kind of foundational. It's just background stuff. But if you go back to your mechanics of materials course, go back to the chapter on stress transformation. That's what this is. This is more circle stuff. So if on the XY coordinate system, I have no normal forces, I have only shear stresses, then I can take the XY coordinate system and rotate it to an X prime, Y prime coordinate system. And lo and behold, there is a normal stress hidden in that rotation. It's hidden in there. You don't see it here, but if you rotate those axes and solve for the rotated normal stresses, it's, excuse me, it is hiding within that stress transformation. And the concrete finds it because this tension is the weakest direction for concrete. So concrete doesn't know nothing about stress transformation, but it will find that weakest direction and crack to that weakest direction. Does that help?
Yes, and you're referring to Morse circle?
Yes.
Okay, thank you.
Okay. Okay. Oh, and that, of course, I explain it and then I say it. Though the element has only shear stress in the XY coordinate system, when transformed via Morse circle, diagonal tension is revealed. So that's how I document it. Concrete is much weaker in tension than in shear, thus the shear failures are really diagonal tension failures. There are many formulations and theories that try to capture the very complicated behavior of beams in shear. ACI 318 takes a fairly simplistic and conservative method to determine allowable shear. And of course, that's going to be the method that I teach you. I just want you guys to understand that when it comes to concrete design, we have all these different models to try to explain different behavior. We talked about the Whitney stress block. That was just a model that simplifies flexural behavior. Well, even more so with shear design, there are dozens of different ways to model a beam in shear, and none of them are perfectly correct. In fact, none of them are correct, but none of them are totally horrible either. They're all just different models that get different degrees of accuracy in predicting shear behavior. But the real behavior, what the beam really, really does, is super, super complicated. And we don't really need to get into how complicated it really is, because we're just going to look at it from the code perspective, which is fairly simplistic. Concrete beams may or may not have vertical shear steel to reinforce the allowable shear strength. We will cover shortly when beams are allowed to not have shear reinforcement. ACI 318, section 9.531 refers the user to 22.5 for shear strength. Chapter 9 is the beam chapter. Chapter 22 is the sectional strength chapter. So a lot of what they tell you in 9, they jump you to 22. ACI section 22.511 specifies that the nominal shear strength of a beam, V sub n, is equal to the contribution from concrete alone, V sub c, and the component from the shear steel, V sub s. Okay, so V sub n is a nominal capacity. Just like M sub n is the nominal flexural capacity, V sub n is the nominal shear capacity. But we have two components. Flexural didn't. It just had the one component, but shear has two. If you had no shear steel in this beam whatsoever, it would have a sizable strength, a significant strength, just from the capacity of the concrete. But if you took the same beam and put shear ties in it, then you're going to get even more strength. So we add the two components together. For the strength due to concrete alone, V sub c, ACI 318 section 22.551 offers a simplified equation and a more detailed method based on table 22.551. The simplified equation can be quite conservative, but it can always be used. It's always applicable. And that equation is V sub c is equal to 2 times lambda square root of f prime c BWD. That's the simplified equation. Where lightweight concrete shear factor lambda, we talked about this lecture 1 or 2, I think it was lecture 1. So if lambda equals the design, or gamma, I'm sorry, that's gamma. If gamma equals the design density of concrete, then for all lightweight concrete, gamma is less than 110 pounds a cubic foot. Lambda is equal to 0.75. If you have sand lightweight concrete, where gamma is between 115 and 125, lambda is 0.85. If you have normal weight concrete, lambda is 1.0. Linear interpolation can be used between the classes. So that's lambda. Most of the time, lambda is going to be 1, but there are situations where you use lightweight concrete that makes it less. V sub W is the width of the beam or the web of an I-beam or the T-beam. And D is your effective depth of your flexural reinforcement, as we've been using it all along for flexural design. ACI 318 table 22551 offers a more detailed method for calculating V sub C. And you can use the lesser of A, B, or C, where A looks like this, B looks like that, and C looks like this. So you can get a sizable increase in allowable shear by going through the rigors of going through these equations. It requires a little bit more input, VU, D, MU. You need rho sub W, which is just a steel ratio based on the stem. Or you can default to this, but 3.5 is quite a bit more than 2, but you have to go through these in order to use those. And ACI 2256 covers V sub C for pre-stressed members and members with axial compression. We are going to touch on this when we get to columns, axial compression. And 2257 covers members with a significant axial tension, which we're not really going to cover in this course. For the scope of this class, we're going to stick with the simplified equation, 2 square root f prime c. Any questions so far? Okay. ACI section 9511 item B prescribes that phi Vn has to always be greater than Vu. Okay, here's your flag, here's your tip-off. When you're doing shear questions on homeworks or exams, you're not done with that problem until you prove to me that phi Vn is greater than Vu. Same as phi Mn and Mu. ACI 318, 21.2, and table 21.2.1 prescribe that phi is equal to 0.75 for shear. It was 0.9 for flexure, it's 0.75 for shear. Any guesses why? Why is it such a penalty on the shear design? Anybody? Uncertainty. Yes, that's a big part of it. Absolutely. So partly why it is such a hit on your capacity. Flexure, you take a 10%. This is a 25% hit. Part of it is uncertainty. The uncertainty of it is that the actual shear mechanism is very complex. And so anything with complexity has uncertainty. The other part about this is that beams, if they were under-designed and they fail in shear, particularly if they have low amounts of shear reinforcement, it can be a quite sudden and brittle failure, a very devastating failure because there's no chance of evacuating a building. So again, anything that has a sudden or brittle type of failure is going to have a fairly low phi factor. So that's the other part of it. Okay, shear steel. Shear steel comes in the form of shear ties. And here is a picture of the shear ties. Now, we've been talking about these because you needed to know about shear ties so that you could calculate how wide a beam needs to be in order to fit in a certain amount of steel. And you need to know how big the shear tie is so that you can make an approximate how deep is D. Where's the center of that steel is kind of based on how big that shear tie is. But now we're actually going to be using these ties for design. So these pieces of steel are actually a design item. They can be hoops as shown, or they can be U-bars. A U-bar would have just the shape of a U with some hooks on the top, like that. So the steel is orientated vertically and it wraps around the flexural steel. So it always comes down and around your flexural steel, and then it has to go up to very near the top and be anchored in some way at the top, because it is this length of steel along the sides that really counts. So this is known as a leg. This is a leg, this is a leg, this is a leg. So this beam here has 2 legs of shear steel. This beam has 2 legs of shear steel. For shear steel, the horizontal pieces don't really count. That doesn't really add anything to your shear design. It's only the vertical legs that are helping to resist the shear. Any questions about that?
Will they always have 2 legs?
No. They usually have at least 2 legs, but we do joists that are fairly narrow pieces of concrete, and we just have 1 leg right down the middle. And we will also do beams. I've done beams on occasion that had so much shear on them, I couldn't make them work with just 2 legs. So I added another hoop here in the middle to get 4 legs. So that's a great question. It won't always be 2, but you can, it's again, the vertical legs, you count how many vertical legs you have for your design. Ties are typically made from number 3, number 4s, or occasionally number 5s. Very, very rarely would you see number 6s. It's just too hard to bend a number 6 and get it to fit into a reasonable size beam. But if you're into, I don't know, like Caltrans, if you're designing overpasses and those monster beams that are spanning from column to column, you know, the one that comes into mind is when you're going down the 91 freeway and you're heading west, if anybody does that freeway route, when you go under the 241, they've got this beam. It's got to be 6 feet wide and maybe 12 feet deep. Maybe that beam would have number 6s for ties. That gives you an idea how big the beam has to be before number 6s make sense. Ties can also be formed by bending welded wire mesh. So welded wire mesh is where this is formed out of wire and it has cross wires welded to it. And then you bend it into this shape. You can use those as well. Okay, so here's my beam. And I don't want to say it's failing, but it's cracking in shear. This is my shear crack. Remember, it goes at a 45-degree angle. And if you notice, this shear crack is crossing 1, 2, 3, 4 shear ties. So I've got 4 sections of steel times 2 legs each that are holding these 2 halves together. So looking at a side view, we see that the stirrups provide a tension tie across the crack interface. So these ties basically staple the beam together and hold it together against the load that's trying to separate. If I recognize that D is from the top of the beam to the center of the flexural steel, as it's been all along, then this is D, and my spacing of ties is S, then I can see that the strength contribution from the shear ties is equal to the strength of one tie, which is A sub V. A sub V is the area of your shear steel, times Fy sub T. Y sub T refers to the yield of the shear tie, times the number of ties crossing the crack. Okay, so approximately N, the number of ties across this crack, is equal to D divided by S. Therefore, the total strength due to the steel ties equals V sub S is the strength according to the shear steel, is equal to the area of the shear steel, the yield of the shear steel, times D over S. AV is the total area of one shear tie, but in this case, I have 2 legs. FYT is a yield stress. D is the same D from the flexural analysis. S is the spacing of your shear ties. So ACI 22511 specifies that V sub N, your nominal capacity, is equal to V sub C, which we just learned is 2 square root F prime C times BD, plus V sub S, which we just learned is AV FYD over S. Section 9.5.1.1 prescribes that phi Vn is greater than Vu. So phi Vn is equal to phi Vc plus phi Vs. Has to be greater than Vu. And phi is 0.75 for shear. The same phi applies to both Vc and Vs. So ACI 9432 prescribes that the maximum design shear Vu can be taken as the factored shear found at D from the face of support if all of the following are true. And by the way, we kind of shifted here a little bit. So we were talking about the capacity Vc and then the capacity of V sub S. Now what I'm talking about is how do you find your demand V sub U? And the demand V sub U actually is not equal to your maximum shear on the beam. ACI allows us to take the maximum shear at a distance D from the face of support, but only if all of the following are true. So A, your support reactions in the direction of the applied shear introduces compression into the end region of the beam. Loads are applied at or near the top surface of the beam. No concentrated loads occur between the face of support and the critical section. And so, the support A reaction causes compression. So the support is pushing up at the bottom, the load is pushing down from the top, so I have compression from the top to the bottom. That's A and B. Loads are applied at the top of the beam, and I have no concentrated loads here at the very end of the beam. Those are my constraints. If all of that is true, then on my shear diagram, My end reaction is R sub u, my reaction factored R sub u. But I don't need to take the shear at the end. I can take the shear at D from the end. So I use similar triangles and calculate what VU is at D from the end, and this becomes my design shear. Does anybody have any questions about that?
Yeah, can you explain again why it's not linear? What I would think, just because it's a uniform load.
Okay. The shear diagram is linear. What the code is allowing us to do, and I think I might have not done this very clearly, but if I go the distance, this distance right here is D. So if I go that distance out from the end of the beam here, and I go straight down like this, what the code is saying is that I don't need to design for RU. I can design for VU, which is here, right there. So if I design for VU, then that means I don't have to design for any load higher than this. So it basically takes the points off of your shear diagram. That's what it means. So if I go to the next slide, pardon me, if I go to the next slide, okay, that's how I got that. Did that help, Robert?
Yeah, that cleared it up. Thanks.
Okay. And basically what the code is saying is, I'll give you a reason why it does that. That doesn't seem to make sense, but why is it doing that? And that is because if the beam is going to fail in shear, it's going to fail along this line. So any load that is to the right-hand side of this point goes into the bottom portion and is trying to pull these two apart. Any load that goes into the top between the line and the end, these loads are actually going straight into the reaction. They're not loading across that crack. They're just going in compression straight into the reaction. So there's no need to design for this last little bit of load because it's not loading up that crack. So that's why we're ignoring that last little bit of load and only designing for VU here. Okay? Does that make sense to everybody?
Yes.
Okay. All right, so the next thing we're going to say, as you progress towards the center of the beam, the shear is decreasing, as you can see. Eventually hitting zero at some point, usually midspan for uniformly loaded beams. So right here at the midspan, if this is all symmetric, you have theoretically zero shear. So as the shear is dropping off, so is your shear demand. So VU decreases as you get towards the center of the span here. So you actually, there's not just one VU, there's a VU at any given section. And it's our job as designers to make sure that at any given section, we have at least enough VVN to cover the VU at that section. So, but what it also means is that we can start dropping off shear ties as the shear starts dropping off. ACI 9631 specifies that the minimum shear steel must be provided at all locations where VU is greater than or equal to half of VVC. So if VU is still greater than this line right here, this line right here is representing half of VC, as long as VU is greater than half of VC, the code, the code requires that you provide at least minimum steel. If VU is less than half of VC, as it is right here in this region here, then you could theoretically drop the ties altogether and not provide any shear steel. That's what the code says. Okay. If, however, the VU is greater than half of VVC, then ACI 318-9633 and Table 9633 require the greater of, and this is your minimum steel requirements. So AV min over S is equal to 0.75 square root F prime C BW over FYT, that's 1, or AV minimum over S is equal to 50, this is really PSI, over BW FYT. Whichever of the two that is greater, as I say here, greater, that's your minimum steel requirement. If VU is greater than half VVC, then ACI 318-97622 and Table 97622 prescribe the maximum spacing of transverse shear reinforcement as, so this is area, this is going to be spacing. If V sub S, and this is V sub S required, is less than 4 square root F prime C BWD, then the maximum S spacing is either D over 2 or 24 inches, whichever is less. If V sub S is greater than 4 square root F prime C BWD, then your maximum S spacing is D over 4 or 12 inches. Okay, this VS is as required by design, not VU. So we'll do an example of how you calculate the VS that goes into this, but there's no fee factor on this either. This is a required VS. So basically what the code is doing is they set this threshold. This is a stress level. And if the stress is less than this threshold, then you're pretty lenient. You can have your ties as far apart as 24 inches or D over 2. If, however, you are above this stress level, it's pretty stressed. And so regardless of the strength demands, you can't place your steel any further apart than D over 4 or 12 inches. A third limit on spacing can be derived based on the required strength. So if VVN is equal to VVC plus VVS, like we said, which must be greater than VU, then VVS is equal to VU minus VVC, just rearranging these. So VS is VU minus VVC over phi, and V sub S is ASFY D over S equal to the same. So now I can solve for S. S required is AVFYD over VU minus VVC over phi. So that's 5 different ways to calculate your maximum spacing of your shear ties. Okay, like we talked about on beam heights, we said beam heights have to be some buildable some buildable number. Well, the same is true with the magnitude of S. S is usually specified in half, 1, or 2-inch increments. Half-inch increments are usually only if your spacing is at or less than 4 inches, and 2 inches is usually for S greater than 12 inches, more or less. So in other words, do not tell the construction crew that you want number 4s at 3 5/8 inches on center. Again, they will come at you with a shovel. Tie spacing is usually tiered, so the smallest S occurs near the end regions with the highest shear, and then S may be increased for middle sections. 2 or 3 tiers at most is optimal. Repeated that one. And lastly, ACI 22512 limits your maximum allowable shear to phi times VC plus 8 square root F prime C BWD. So in other words, there's a maximum. You can't just keep pounding in more and more and more steel. Eventually, the thing's going to fail without even yielding the steel. So this is your maximum. ACI 2224A limits shear reinforcement usable yield for rebar to 60 KSI, even if actual rebar grades is higher. This statement right here, 80 grade steel is becoming more and more common and available. But even if you use 80 KSI steel for your shear ties, you still can't design for more than 60 KSI for shear ties. Okay, I think I got a few more slides for tonight. This is your procedure. You draw your factor shear VU diagram, calculate VU at D from face of support, calculate phi VC. This doesn't really have any unknowns in it, so you can calculate this straight up. Stirrups are required if half of phi VC is less than VU. Find your spacing requirements due to strength. Check your maximum spacing. These two are based on the minimum shear steel. And if VS is less than 4 square root F prime C, you have D over 2 or 24 inches. If it is greater than 4 square root F prime C over BD, then it is D over 4 less than 12 inches. Then you confirm that your VU is less than this maximum. Okay, and I don't want to get into the example. So when you download this presentation, I think this is going to be very helpful for you. This is on slide 134. We'll cover the example when we come back to this on Thursday. But slide 134 has this kind of summary of the whole procedure. And when we come back, we'll do an example that walks you through numbers with this procedure. Okay, so do we have any questions so far? Okay, so I can stop sharing. And are you guys able to actually see me now?
Yep.
All right, here we go. You can almost hear, Willow, come on, sit. Oh, you're not gonna perform, are you? Sit, come on. All right, I have to do this the hard way. There is my 10-year-old dog who doesn't want to perform anymore. Come on, Willow, do something exciting. You barked earlier. All right, well, there's my black lab. And as you can tell, that's pretty much the end of the academic portion. Okay, to rub the belly. She'll get one in a minute. To them person who submitted homework late, yeah, I got your email. So I'll look at the one that you emailed for your homework. Do I have any last questions for tonight's before I log out? Any questions at all? Do you have any other pets? Yes, my wife has a Maine Coon cat who is just getting obese. And then I have a short-haired domestic cat who's going on 17 years old now. So that we're down to 3. Any other questions about concrete? Okay. Well, hopefully this makes it a little bit less dry and less academic. Of course, I will have office hour on Thursday at 4 o'clock. Please try to get to the homework so that you can have some questions for me. And other than that, we will pick it up on Thursday. Thank you, everybody.
Thank you, Professor. Oh, Professor, quick question. Do you have office hours on Tuesdays too, by any chance?
Tuesdays and Thursdays, yes.
Okay, perfect. Thank you.
You're welcome.